All right, welcome back, ladies and gentlemen. Looking at 3.4 today, our zeros of polynomial functions. We're going to be looking at the PRR. You might remember that from last year. Some complex zeros and something called linear factorization. All right. So first of all, we're going to start with that linear factorization theorem. We're going to say if you have a polynomial of degree n. So you got to remember that the degree is the largest exponent. So if it's a quadratic, the largest exponent is 2. If it's a cubic, the largest exponent is 3. That's the degree of the polynomial. And if you have a polynomial with a degree n, where n is bigger than 0, we don't deal with anything less than 0, then f has precisely that many factors. So a quadratic has 2 factors. A cubic has 3 factors. A quartic has 4 factors. That's the idea of this particular theorem. Meaning we can take a function, f of x, and we can factor out this leading coefficient, which is kind of something we'll do here later. And we can just write it as a whole bunch of linear factors. Notice these are all linear factors because it's x to the first power. And all of these c values are complex zeros of the polynomial. Either numbers like we could have c equal to 3. We could have c equal to -7. We could have c equal to the square root of 6. And later on, you'll realize that also means we have a negative square root of 6 also. And there we could have 2 plus I. We'll get to these a little bit later today as well. We could have 3 minus root 2. We could have all sorts of different answers as our zeros. And these are all complex zeros. So we have real ones, which is all of these except for this one. The 2 plus I is imaginary or complex. We could have irrational numbers, so our square roots and that sort of stuff. Okay, so what we're going to do is we're going to look at what this means. If I give you a quadratic function, just go really simple here, because this is something we could factor without anything too hard that we don't know how to do yet. So if I gave you a quadratic function, x squared plus 3x plus 2, most of you could probably tell me that this is going to factor. Actually, by the theorem, it tells me that has to factor to at least 2 factors. It doesn't even matter if they're nice numbers or ugly numbers. In this particular case, they're nice numbers. And it factors to x plus 2 and x plus 1, which gives me -2 and -1 as zeros of the function. Remember, I'm kind of describing things we know already. The other part that we might remember from previous lessons here recently is since those two numbers are zeros, that tells me that if I use them in division, either synthetic division or long division using these 2 factors, if I use those in the division, I will get a 0 as a remainder, which means it is a 0. All right. So this is the kind of the big thing for today, the rational zero test. You might remember this last year is called the possible rational roots. So some of you might be groaning right now. Some of you might be going, I don't know what the hell he's talking about. But either way, we're going to really study this particular test. Now, nobody really seems to like this definition for this because of this long polynomial. But what this is, this f of x is actually how we would describe all polynomials. Quadratic, cubic, quintic, anything. They all look like this. Where this right here, this first term is our biggest degree. Then we have the degree below it. And then there's a whole bunch of other things all the way down to quadratic, linear, and constant. So this right here, by the way, I think I mentioned this in just a second. This is our constant term. It's just a number, like 3 or 7 or 12. Okay, and I hope all of you know exactly what this thing is. That's our leading coefficient. Okay, so if you have a polynomial that has integer coefficients like this, an integer means non-fractions. It's the numbers you see on a number line. Then every rational zero of f has the form this. This is p over q. This is the same thing as what you remember from last year, p over q. And p and q have very special roles. P is the factor of the constant term. All the factors of the constant term. So sometimes there's lots, sometimes there's not so many. And q is the factor of, or any factor of the leading coefficient. All right, we're going to be using this quite a bit. And I'm even going to upload another video with a whole bunch of different examples of using this and using some of the other things that we're going to go over today. So for this particular problem here, we are just going to list the possible rational roots. The possible zeros, basically. Now, this is a quadratic function. We know there should be two answers, but that's not the idea for this particular example. What I want to do here is I just want to know what is my list of possible rational roots. And I start off with just making a list of p's and q's. Now, p is, from the last page there, all of the factors of -6. Everything that goes into -6 evenly. So we know it's 1, 2, 3, and 6. Now, it's not just the positive versions. It's both versions, plus and minus, for all 4 of these. All right, so that's all of my possible numerators for my rational roots. And then my denominator here is all of the factors of the leading coefficient, which is 1, which is nice because when it's 1, it makes it super easy because 1's the only choice. So the list of all possible rational roots is every combination of this fraction. So I have a plus and minus 1 over a plus and minus 1. So I get a choice of plus and minus 1. I then get to do 2 over 1. So it's plus or minus 2. Then I look at 3 over 1. Oops. Plus or minus 3. And then I do the same thing with 6. So you'll notice there are 8 possible rational roots for this particular quadratic. And you might look at this problem and go, well, this isn't factorable, which means it's probably no rational roots, which is right. Okay, but the idea is just to list all possibilities. All right, same for this one. Just want to list all of the possibilities. So PRR, again, I still have just P over Q is equal to all of the factors of 4, plus or minus 1, plus or minus 2, plus or minus 2, but I don't need that again, and plus or minus 4. All over all of the factors of 3. Well, 3 is kind of nice. It's just plus and minus 1 and plus or minus 3. Now I need to make a list of all possibilities. So I just start with the 1. I go 1 over 1, which means I get a plus or minus 1. 1 over 3. I get a plus and minus 1 over 3. And I just continue this process. Now I've taken care of all of the 1s over both of these. Now I'm going to go to the 2s. So 2 over 1. And 2 over 3. And then I go to the same thing, do 4. So plus minus 4 and plus or minus 4 thirds. So now notice we get 1, 2, 3, 4, 5, 6 times 2 because it's plus or minus. There are 12 possibilities for this particular cubic function. There are 12 different possibilities. Now coming up, we will be looking for actually finding the rational roots. Oops, let me get rid of that writing there. This one's a little bit longer because of the type of numbers that we have here for our leading coefficient and for our constant term. But if we look at the p's over the q's, we get, for p, all the factors of 12. So 12 is kind of an ugly number for us because we get 1, 2, 3, 4, 6, and 12. And then 10's not as ugly, but it still does have more than we've had in the last couple problems. So 1, 2, 5, and oops. $10. Well, this list is going to be long. Oops. Okay, so we go with the 1 first from the numerator and then put it over all of those denominators. So we get 1, and I'm not going to write plus or minus, but you have to understand that they are all plus and minus. So we get 1, 1/2, 1/5, and 1/10. Then I take the 2, and I go 2 over 1. Then I go 2 over 2, which is 1, but I've already taken care of the 1, so I'm not going to write it again. Then I get 2/5, and then I get 2 over 10, but 2 over 10 is 1 over 5, and I already have it, so I'm not going to list it again. Then I continue with the 3. 3, 3 over 2, 3 over 5, and 3 over 10. You notice now we're only halfway done. All right, going to the 4, I get a 4 over 2. But 4 over 2 is the same thing as 2, and I already have it, so I'm not going to repeat. Then I get 4 over 5. And then I get 4 over 10, but 4 over 10 is the same thing as 2 over 5, and I already have that, so I'm done with the 4s. And then I go do the same thing with the 6. I get 6. 6 over 2 is 3, I already have it. I get 6 over 5. And 6 over 10 is 3 over 5, and I already have it. And then I move on to my 12. 12 over 1, 12 over 2 is 6, I already have it. 12 over 5, I don't have. And 12 over 10 is 6 over 5, and I already have it. That means that was my last number. And if you count that up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, did I count wrong? 4, 8, 12, 16. There are 16 different numbers, each with plus and minus, which means there's 32 different combinations, or 32 different possibilities, and there's only allowed to have 3. All right, so let's move on to actually finding some zeros. So we're going to use the PRR to factor this cubic function. So we are going to say, all right, let's look at the PRRs. We're going to get plus and minus 3, plus and minus 1. I know I did that out of order. Sorry. Plus minus 1, plus minus 2. And I get 1, 1/2, 3, and 3/2. Now, we really hope it's not a fraction. So what I always tell people is I say, let's try 1 or -1. And what I mean by try is, as I mentioned, something about division. If it's a factor, it will go into the function through division. So I'm going to use some synthetic division with a positive 1. Oh, always make sure you got the right variables here. I have a 3, 2, and a 1, so I'm good. I don't have to add any zeros. All right, so I go 2, 2, 5, 5, -3, -3, 0. Well, that was super, super nice, super easy. I got the first one on the first try, which means, now this 1 is a 0, which means x minus 1 is a factor. All right, because 1 is a 0 of this factor. Oh, where'd it go? What I'm going to do is I'm going to change the color here. So I get x minus 1, and then I get times the leftover piece. This is 2x squared plus 5x minus 3. Once you get down to a quadratic, you have your choices to go about it. You can either quadratic formula or you could factor. I really hope this one factors. So if I said 2x minus and 2x, oh, not 2x, x minus, I think a 3 goes there and a 1 goes there. I get a plus 6 and a minus 1 makes a plus 5. That means all of my zeros are x equals 1, x equals 1/2, and x equals negative 3. And notice all three of those numbers were on this list. So in this case, we got some pretty nice numbers. All right, so notice we did factor, and we actually went down to linear factors, kind of like the theorem says, we went down to linear factors. So one of the next things we're going to look at is the idea of a complex zero or imaginary. Now, we have these imaginary numbers that we've dealt with a little bit, a plus bi, and whenever this number is a zero, you also get its conjugate. And the conjugate just means, let's say 3 plus 2i is a 0. That means 3 minus 2i is automatically a second 0. And this is handy for us because it actually is going to help us solve if you're given an imaginary number as an answer. What I'm going to point out also is this is not imaginary numbers, but it also goes for irrational zeros as well. So if you have an a plus bi, or sorry, an a plus root b, you also get a minus root b. And this comes in handy when we try to write polynomials later on as well. And I kind of point out here the quadratic formula. You know the quadratic formula is opposite of b plus or minus the square root of. And that kind of takes care of the conjugates. You get the plus version and the minus version. All right? So here's something that we're going to do. We're not going to use synthetic division here, even though you can. Synthetic division gets a little bit difficult. But what I'm going to do is, since I know that 1 plus 3i is a 0, so is 1 minus 3i. Now what I'm going to do is, I know that since they are zeros, I can write them in factored form, and I can FOIL these two things. And I can FOIL them. I can say, okay, x squared minus x times 1 minus 3i minus x times 1 plus 3i plus 1 plus 3i times 1 minus 3i. I know this is long, but it's something we've done before. So I get x squared minus x plus 3ix minus x plus, oops, sorry, not plus, minus 3ix plus, here you got to FOIL this complex number here, so you get 1 plus 3i minus 3i minus 9i squared, which means a plus 9. And then I'm going to simplify. I'm going to write this down here a little bit. I'm going to say, okay, x squared minus x is minus 2x. This goes away with this. This goes away with this. And I get 1 plus 9 is 10. Now, the reason I did this is because since both of these are factors, the x squared, this quadratic, is going to go into this quartic. So I'm going to show that it goes into the quartic by doing some division. So I can figure out what the other quartic is. Sorry, the other quadratic, not the other quartic. What am I thinking? All right, so some long division, just kind of follow along. We did this already. Oops, what did I do here? Oh, that's supposed to be a cubic. Oopsie. Okay, 10x squared. And here I get negative x squared. Sorry, negative x cubed minus 4x squared plus 10x. Get a minus x, which gets a negative x cubed minus plus 2x squared minus 10x. So here I get a minus 6x minus, or plus 20x minus 60. Oh, where did that 10 come from? Jeez. I need somebody bopping me on the head, apparently. That's not a 10, that was a 2. All right. 2 minus negative 10 is a plus 12x. And you'll notice that this is now 6 times as much, or negative 6 times as much. So if I hit negative 6, that means this polynomial here is equal to, my answer is x squared minus 2x plus 10 and x squared minus x minus 6. Well, I already know the two answers from the first quadratic. The second two answers, this is actually factorable to x minus 3x plus 2. So my zeros, notice this was a kind of a long problem. This is why actually we're going to spend a couple days here. My zeros are 1 plus or minus 3i and 3 and negative 2. And it was just for all of that. It was just for those 4 answers. But these long problems, if you've gotten to know me so far, these are the problems that make it worthwhile to do mathematics. 2 plus 3 is no longer worthwhile. It should not be stimulating your mind anymore. These should be stimulating your mind, kind of working that muscle if you think of your brain as a muscle. All right, so this particular example, same kind of idea. The problem here is you don't get automatically to know what a 0 is, so you're going to have to start with the possible rational roots. Oops, ugly P. Okay, so R. So possible rational roots are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, all over 1, which means it's just these 4 numbers. So I hope 1 works. I hope you don't think 1 always works, but I think you guys will get that. Pay attention here that I don't have a quartic, so I need a 0 piece here. And a 1, a 2, a negative 12, and an 8. I really hope this works just because make it a little bit shorter. So 1, 1, 1, 2, 2, 4, 4, negative 8, 0. Yay, apparently I chose really good problems. Now, here's the issue. All you've determined is this is now x minus 1 times x to the 4th plus x to the 3rd plus 2x squared plus 4x minus 8. Which means now you have to keep going with synthetic division. Now, I always try the same number again, just to hope that it works. Because you can repeat zeros. Remember, multiplicity, it's possible. So I go 1, 1, 2, 2, 4, 4, 8, 8, 0. Oh, man, this is looking pretty good so far. So x minus 1, and I get another x minus 1. But then the problem now is I get an x cubed plus 2x squared plus 4x plus 8. Which means that's a cubic, and you have to do it again. Dang it. All right, so let's find another color here. Now, I can guarantee you that positive 1 will not work because there's no negatives in here to get rid of the positive. So I'm going to try, hopefully, negative 1. We get 1, negative 1. Oops, forgot my bar. 1, negative 1, 1, negative 1, 3. Dang, that negative 3 is not going to get rid of that. Dang it. Okay, so the 3's not, or the 1's not going to work. Now, notice this is what I'm doing. All I did was erase. If you're using a pencil like you should, whoa, what happened? If you're using a pencil like you should be fine by erasing. So -1 didn't work. Let's try -2. So I get 1, -2, 0. 0, 4, -8, 0. Oh, that's super nice because now I'm almost done. I get x minus 1, x minus 1. I have a -2, so I have an x plus 2. And then I have a leftover x squared plus 4. And so I have some zeros of x equals 1, 1, -2, and this piece with x squared plus 4 equals 0. X squared equals -4. If I square root both sides, I get x equals the square root plus and minus of -4, which means x is plus and minus 2i. Notice I get 5 answers, which means I'm done, which means I can move on to this last slide and finish this video. There's a lot of stuff on this last slide here. We are going to spend a couple days in class working on this. We're going to spend both Friday and Monday on this. So you guys kind of have a longish assignment. Friday, we're going to spend on those 8 problems. Over the weekend, I hope you complete the rest of the assignment and maybe even do some extra ones just in case. And Monday, I expect to be working on those other 8 assignments. And there'll be a quiz on 3.4 on Tuesday. And this is all on your paper. All right, have fun doing the math. I hope you get some good stuff out of this today.